Okay, next we're going to speak about the SNMP, or what it means, the Simple Network Management Protocol. So by the name, it's a very simple and useful protocol for network management. Now, in SNMP framework, we have two roles: the SNMP agent, which is going to be the network device being managed. So all CISCO devices and all network devices have built in the support for the SNMP agent. And the SNMP manager, which means it's going to be the application or the SNMP server who is used to manage the agents. SNMP has three versions: V1, V2C, and V3. Now, the main between V1 and V2C, it's a lot of, let's say, functional differences. But between V2C and V3, it's mainly security related differences and of course additional capabilities. But this class, being a security class, we're going to speak about, of course, the added security capabilities of V3 as opposed to V1 and V2C. Now, the SNMP server or the manager uses the concept of MIB, or Management Information Base, in order to read status or health information from a network device, or in order to change the configuration of a network device. So via MIBs, what that means is that how SNMP agent looks like on the devices is like a tree. So the MIB is going to be like a tree with a root in there, and we know that a tree is not looped, right? So it's going to be a non-looped tree, something which is non-looped, and from the root, which has a object identifier. Likewise, we have, for example, let's say the interfaces of the router, which has an object identifier. We have the, let's say, what else? Interfaces. Next, let's say the CPU, which has an object identifier. And then from the interfaces, we have, of course, another segment for each of the router's interfaces, like gig 00, gig 01, gig 02, and each of them have other object IDs. This is the MIB. It's a tree of objects which is used by SNMP to be able to either read information from the MIBs, like CPU information, CPU load, or memory load, and to also change the configuration of the device. You can also configure the device via SNMP. So what's going to happen is that when, assuming that server A is the SNMP manager, and let's say SH3 is the SNMP agent, the device being managed. It means that if server A wants to read load information about gig 00 interface, it means it's going to parse this tree top down, and it's going to stop on the object ID, which identifies that interface, and read the information from there, like what is the load of that interface. So SNMP functions are based on three main operations, because we can read something from the device, or we can write something to the device. We're going to have SNMP get, SNMP set, or SNMP trap. Now, the SNMP get function, as the name states, the server wants to get some data from the agent, which means the SNMP get function is used by the server to read device statistics for appropriate MIBs from the agent, which means like interface load, memory load, CPU, and so on, and show you that in a graphical format on the SNMP server. Which means to do the get action, we need only read-only access to the managed device or to the SNMP agent. And the SNMP get function is going to run over UDP port 161. Now the set function, as the name states, is that the server wants to set something on the managed device, which means the set action is used by the server to configure the device. Like one commonly known such configuration supported by SNMP is going to be like VTP configuration. So from the SNMP server, you can actually change the VTP configuration on the SNMP agent, which is going to be a switch. Because we want to change the configuration, it means that the server requires read-write access on the remote device. And this also runs over UDP 161. We also have the SNMP trap, which what this is used for is that the server receives this time unsolicited events from the managed device. Like when an interface is down, when the BGP adjacency goes down, or when the EdgeRP adjacency goes down, you would want the agent to signal that to the server. So likewise, you're going to have an event happening on the server, which is going to show you in a graphical format that BGP adjacency is gone on router whatever. Which this means that this SNMP trap partially overlaps in scope with syslog. And let me convey that as double width in there. So this means that it's partially overlaps in scope with syslog, because of course also syslog can detect an EdgeRP adjacency going down and send you a log message, but to a syslog station, not to an SNMP manager. And the traps are running over UDP 162, can optionally use TCP, and this is called informs, not traps. Now it makes sense that the set and the get actions run over one UDP port, because those let's say functions are initiated by the SNMP server, while the SNMP trap is something initiated by the SNMP agent. So it makes sense it uses a different port number to easily differentiate between who initiated that kind of session to begin with. Now we also have in SNMP something which is called SNMP views. So what I said before about the set, get, and trap and the views, all of them are supported pretty much by all SNMP let's say versions. SNMP views are used to limit access to MIB information on the managed device. Because, for example, you may not want an SNMP manager to be able to read everything, all the informations, all the MIBs from a device. You may want a manager to be able to read only the interface load and the CPU load, but nothing else. So that's being controlled via views, and also the name tells you exactly what it does. An SNMP view allows a manager to view only some of the MIBs, which means to have access to only some of the MIBs in there, which means to read or to write, to change only parts of the router's MIBs in there, not all of them. We have three view types: read views, which are being used for get actions. So when the router reads something from the managed device. Write views, which is for set actions, when the SNMP manager configures or sets something on the managed device. And notify views, which clearly makes sense for those are used for traps or informs action, when the agent is going to notify the manager about something going on, like via a trap or an inform. Now, we're going to speak about SNMP version 3, and I said that it mainly adds security features to V1 and V2C. Now, V1 and V2C, in V1 and V2C, authentication between the manager and the agents was via a community string of type read-only or read-write, depending on which kind of actions would you want the manager to take on the agents, set or get. But the community string was sent in clear text in SNMP packets, and there was no SNMP packet encryption. So clearly this is not secure, because if, looking back at this diagram, if server A is my SNMP manager, and I want to manage via SNMP router 1 to read some of the router 1's informations, interface load or CPU load or whatever. Oh, this is the agent, the managed device. When server A sends a set action or a get action to router 1, in those packets is going to put in there the community string, or which is nothing else but the authentication string, like a pre-shared key. But it's going to put that value in clear text, which means if somebody in the transit path, like somebody sits in here in the transit path, an attacker, it's in the transit path, and captures the SNMP packets, is going to be able to see the community string in clear text, which means the attacker can also then go and manage a device. So it can go and have set or get actions to that device. Of course, we can go on the managed device on the agent and restrict from which sources, and tell the SNMP agent, like the router being managed, who can connect to you for set and get actions, but that's not built in. So with just with the regular configuration of V1 or V2C, where you don't restrict on the agent who can actually manage the agent, if the attacker captures the packets in between the server and the agent, it identifies the community string, the pre-shared key, and then by himself he can also go and actually read information from the router, or more dangerously actually change the configuration on that router. So this is not secure clearly. Now SNMP version 3 fixes both of those problems, because first of all, authentication is stronger because it's being done via username and password, no longer via a pre-shared key, and the password is no longer sent in clear text. I'm going to be using hashing to send the password, not in clear text. And also V3 supports encryption of the packets. So with version 3, it means that if this is the manager, SNMP manager, and this is the agent, we're going to see that if we perform only authentication, when server A manages router 1, the password is not sent in clear text. So if somebody in the transit path captures that SNMP packet, is not going to know the password so that he can also get on that router and manage it. But also clearly, if we use also encryption, it means that in between those two, the agent and the manager, likewise we're going to have a secure communication channel which is both encrypted and authenticated. So all traffic flowing back and forth, all SNMP traffic between the manager and the agent, is going to be secured by that secure channel via encryption and authentication with hashing. Actually, just to make sure I have not been misunderstood, so authentication SNMP version 3 performs authentication of the manager to the agent via username and password, but with hashing, not via in clear text. And optionally, all traffic back and forth is being encrypted, but SNMP version 3 doesn't provide, let's say, integrity functions for the encrypted packets. So only encryption. Now, to provide those security features in version 3, we have something which is called security models in SNMP version 3. So based on what is the security level we want to achieve in our network, and of course, as you can imagine, to do both encryption and authentication via SNMP version 3, also the manager has to support that around. So based on the required security level or based on the supported capabilities of the manager, different models can be implemented. We have one model which is called no auth, no priv, which is self-explanatory. It means no authentication, no privacy. So it means that no encryption, that's no privacy, and no authentication means that authentication is done via a username only, which behaves like a community string, which is like in SNMP version 2C. So why is this option in there, you might ask? Because clearly it's the same thing like in version 2C, but instead of a community string, we use a username. Because if we want to use SNMP version 3 in our network, which of course adds other features as opposed to v2c as well, and we want to make use of those features, but our manager, SNMP manager, doesn't support encryption and authentication securely, then this is the best use case we can do in order to make use of the added capabilities of version 3. Next one is going to be auth from authentication, so it's going to be authenticated, and no priv from no privacy. This means no encryption of traffic back and forth, but authentication is being done securely, which means via username and password via MD5 or SHA-1, depending of course what the manager supports and also what the agent supports. And finally it's going to be auth priv, which means we're going to do secure both authentication and privacy, which means encryption is going to be supported via DES, triple DES, or AES. And likewise, username and password authentication via MD5 or SHA-1. So again, the models are self-explanatory, which model achieves what and how does it work. Now, a couple of differences between iOS and ASA. ASA does not support set actions, so no read-write communities. It's a built-in design of the ASA. It's meant to, it's like a security, for security reasons, because we don't want somebody accidentally to manage the ASA via SNMP to change the configuration. Then CISCO decided to say we don't support set actions, no read-write communities. So if the ASA is the SNMP agent, you can only read the MIBs but not change the MIB values. So not change the configuration. And also ASA does not support informs, only traps. Now configuration wise on the iOS, we first of all optionally configure SNMP views, which means if you want to restrict what MIBs can the manager actually see, then you're going to define the views in there. Then what's mandatory, you configure what is called SNMP group of users, because at the group level we define the security model and we optionally configure view access. So we first configure a group of users which can manage this device, and at that level of the group level we define, okay, what is the security model and then what is the view access for this group of users. Then we define the SNMP username and password, and of course we define at the username level the authentication and encryption algorithms, and we bind the username to the group. So at the username level we just define the authentication password and protocol and the encryption method in there. But in the end, we have to bind the username at the group level, because the group, let's say, container, the group object, has defined the security model and the view access. So the SNMP group defines what is the security model, and once you connect to this group, then what kind of access do you have on this device. And then at the user level, you just define, okay, this user is going to use this authentication method, this encryption method, and of course it makes sense you have to bind the username to the group, Because otherwise, if you just leave the username unbound, if you don't bind the username to the group, then how could the router know, okay, those usernames are going to use which security model and what kind of view access? Optionally, configure the SNMP server. So far with this configuration, it means that the SNMP manager can connect to the SNMP agent for set or get actions based on the configured view access in there. Then optionally, you can configure the SNMP server on the agent. This is required only if you want the agent, which is like the router or the switch, to be able to send traps or informs to the SNMP manager. And if you do that, of course, we likewise have to bind the username to be used for those traps, because if router 1 wants to send traps to server A, so when you define the trap configuration on router 1, you have to also tell that configuration what is the username in there. What is the username that router 1 is going to use to connect to that server? Because from the username level, it's going to know the authentication and encryption parameters. So it makes sense that if you want the agent to send traps, when you configure traps, you have to also bind the username. Because otherwise the router doesn't know, okay, and which SNMP user should I use to send traps to that manager. And optionally configure the SNMP local engine ID. Default one can be used. Now keep it simple. The engine ID, engine ID behaves like a OSPF router ID. So why is this useful? So when the connection is being done between the manager and the agent, in the manager database in here, in the manager database, each SNMP version 3 agent, which means managed device, it's known by its engine ID. It's like the name of that managed device. So everything in the database of the manager is going to be tied to that engine ID. Everything which it reads from that router is going to be tied to the engine ID. So I said optionally and recommended you should put a static engine ID on the managed device, even if it has a default one, because if this router breaks hardware and you have to replace it, it means the new router which you put in there, the new router 1, is going to have a different engine ID, which means that when router 1 now connects back to the manager is not going to be able to correlate the old router 1's information with the new router 1's information, because the new router 1 uses a different local engine ID. While if you statically configure the engine ID in the SNMP configuration, it means that it's going to be the same engine ID regardless of if today it's router X and tomorrow, because router X died, we replace it with another router. So if you by default, the local engine ID is locally significant, is going to be different between routers. But clearly, if you configure it manually, it's going to remain the same between when you replace the routers because of a hardware failure, which means the SNMP manager is going to be able to correlate the old router with the new router as being the same router in the end. It's just that it was replaced because of hardware failure. Verification on the iOS. You verify users and groups, show SNMP group, show SNMP users, and verify SNMP servers, show SNMP host, and show SNMP sessions, like what are the active SNMP sessions with a server. From the SA point of view, we configure likewise the SNMP group of users. We define a security model. ASA doesn't have the concept of views in there. We configure SNMP username and password. Likewise, define the authentication and encryption algorithms. We bind the username to the group, so the same pretty much configuration back and forward. And then and on the SA, we have to configure the SNMP server For security reasons, as opposed to the iOS, you have to configure the SNMP server and bind the username to be used for that server so that the ESA knows which credentials or authentication is to be used and which encryption algorithms to be used to communicate with that server. Verification wise, verify likewise users and groups. The command is show SNMP server group and show SNMP server user. Verify SNMP servers, show SNMP server host.